Hi everyone, and welcome to your first higher level topic. Today we're going to talk about oscillations again, something that we did at the very beginning. Remember, there's a particle moving up and down and describes this thing called simple harmonic motion. But what we're going to do is to actually derive the equation for the motion of a point, like up and down, exactly how does x depend on t. And then we're going to use what we know already about circular motion in order to do so. And finally, we're going to use derivatives to find velocity and acceleration in a much easier way than we've done so far, and then calculate the kinetic energy and potential energy of the particle using everything we've derived before. It's going to be mathematically strenuous, but I think at this point you should be able to manage it. I hope I'm right. Okay, so let's get started. So hopefully you remember that if I have a certain spring and I attach a mass to it, mass m, when I pull the mass this way, it's going to feel a force the opposite way, and then when I push this way, it's going to feel a force in the opposite direction. So what it's going to do is, when it's just going to go this way, then this way, then this way, then this way, describing an oscillation. If there's no friction and this is a perfect spring, then the oscillation is harmonic simple, which means that this thing just always oscillates at the same frequency with the same amplitude. Okay. Now, what we want to do today is to give this thing a little bit of math and find out exactly how the position of this guy is varying with time. Varying or varying? Well, either way. Anyway. So, first thing that we need to remember is that this force is proportional to the displacement x. So we put this little k here, which is the constant of proportionality, and this tells us how strong the spring is. So really big K, really strong spring. Really small k, really weak spring. And then we know that if the displacement is positive, so for example here, then the force is actually pointing this way, which is negative. So we need to put a negative sign in here, because this means that the force is always pointing in the opposite way of the displacement. So for example, when we push this way, the force is going to try to get it back to the position of equilibrium. And it's this negative sign that makes the vibration possible. If this wasn't here, then you would get a force that gets bigger with displacement, just making this go further and further and further again. It would never go back. So this is an essential part of our equation. Now what we would like to know now is how can we find out x of t? So x is a function that depends on t, and we know that it's going to do something like this, right? Back and forth. So as time goes by, first it's going to go forward, then backward, and forward, then backward. It's going to keep doing this forever and ever. Now, unfortunately, top of our heads, it's hard to come up with some function that does this. But we do know something that behaves in a very, very similar way, and that is circular motion. So let me show you what I mean by that. Okay, so here I have this little star that's undergoing circular motion. So it's doing this thing like this, going around and around and around a circle of radius r. Okay, so it's doing this thing. And now you may think, what does this have to do with a star that does this and this and this and this? But what we can do is look not at the whole movement of the star, but just look at the horizontal component of this movement. Okay, so let me show you what I mean. So here at the beginning, the star is here. So the horizontal component of the movement is just this much. Right, so let's just draw a little line to show that. Okay. Now after a certain time, my star, oh no, this thing got stuck. Well, I'm just going to leave it there. So after a certain time, my star has moved here. And now the horizontal component is really, so this is supposed to be a dashed line. This is the horizontal component, right, of the movement of the star. So it's moved, really, the shadow of the star has moved from here to here. And as I keep moving the star this way, you can see that the shadow of the star has now moved here. So you can see that the shadow of the star was here, now it goes this way, and then finally when it reaches the top, it will be exactly in the middle. And then as my star moves to the left, then I will have another displacement to the left. So I have a star that went this way and then now it's here. and then the star continues onto here. So now I have a star that went this way, and now is here. And then when it starts going down, what we can see is that actually there's no difference with before, right? That the horizontal component is still this much here. So the star went this way, then bounced, and then the shadow started going back, and then this guy goes over here, and then the horizontal displacement is just here in the middle, and then the star ends up moving back to the same place. So you can see that the shadow of the star is really doing this, 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 which is exactly what something in a spring would do. And we actually do know the equations governing the movement of the star, the circular motion equations. So since we know this, and we know how to calculate the horizontal component of something, like for example, we know how to calculate this thing here, if we know the angle, then things are very easy for us, because we only need to use the equations defining circular motion, then find the component, and then we'll have found the equations for simple harmonic motion. So let's do that. So first, a little refresher. In circular motion, what we were interested in was not so much the distance that something went around, but the angle that something went around. But because what we care about is that this is a circle, right? So this is 0, and then this will be a certain angle, this will be pi halves, this will be pi, and so on. So this thing does a certain angle every second. And we call this thing the angular velocity. Hopefully we remember. So the angular velocity was the increment in angle divided by the increment in time. Now that you know derivatives, what this is really is the derivative of the angle with respect to the time, because this is just the average angular velocity. However, since we're only considering things that are moving at a constant angular velocity, these two things are the same. Good. So now if I wanted to know the angle as a function of the angular velocity, I'd be like, well, the angle is just the angular velocity times the time, right? So if I start at 0 and I do 2 radians every second, then after 2 seconds I've done 4 radians, and after 3 seconds I've done 6 radians. So I'm just multiplying things. So then the angle is going to be the angular velocity times the time. So that's easy. However, this does not cover every possibility, because I could have a movement that starts here, for example, or here, right? So I have to take this into account. So the angle will be the angular velocity times the time. That will give me the increase in the angle, but I need to take into account the initial angle. So to this thing I need to add the initial angle, which I'm going to call theta 0. And that's going to give me the angle of this movement. And so far that's all we need to know. All we need to know is that the angle follows this thing. Now let's forget about this for a moment, and let's just take a specific angle, and I'm going to call it theta, and later on I'm going to replace it by this expression here. But for the moment I'm just going to say, okay, I'm at angle theta here. So here we go, and this is theta. And I'm interested in finding the horizontal component. And why do I want to find the horizontal component? Well, because, remember, the horizontal component of this movement will tell me how this thing is evolving in time. It starts here, then it goes here, then it goes here, then it goes here. This will tell me the equation for the position of simple harmonic motion. Now, instead of using the letter R, which is very good for circular motion, I'm going to use the letter A, which is amplitude. Because, as you can see, this thing here, which is the radius, is also the amplitude of this movement that goes back and forth. So I'm just going to use the letter A instead of R. There's absolutely no difference. Right, now what I would like you to do is, in your notebooks, just pause the video and take 10 minutes to try to figure this out. Can you figure out the horizontal component? So I'm talking about this length here. If I know the amplitude and I know this angle, can you please give me an equation for this length here, which is x, in terms of this amplitude and this angle? And remember, I'm not asking you for a number, I'm asking you for an expression, which means you should leave everything in terms of letters. So pause the video, try it out, and please only come back until you're, like, when you're desperate or you have figured it out. Okay. Hopefully you did what I asked you to do, and what you got was, okay, then x has to be equal to, let's see, so this is A, and this part here is the contiguous side of this angle. Therefore, this times the cosine of the angle will give me x. This is actually A. So x has to be equal to a times the cosine of theta. And now I can just finish this up and be like, okay, cool. But theta is actually changing in time. So instead of theta, I can just put this whole thing in there. So it's equal to a cosine of some angular velocity plus theta 0. And that is the equation that tells us how the position changes with time in simple harmonic motion. Now what's interesting here is that we have an angular velocity, but nothing spinning, right? So it really doesn't seem to make any sense. But this is the angular velocity of the associated circular movement. So if you have something that's going up and down, you can imagine that it's just a projection of some circular movement, and this angular velocity is the angular velocity that the circular movement would have if it existed. Of course it doesn't exist, but this still does the right thing. It gives us gives a way for the cosine to know how to change with the time. In other words, I know that you've done this in math. Well, oops, I left that thing in there. I know that in math you've done cosine functions, right? And you know that cosine functions do something like this. And this is precisely what simple harmonic motion does, right? I have a particle that starts here. This is x, and this is time. And as time goes by, it goes down, then up, then down, then up, then down, then up, and so on and so on and so on, which is exactly what this function does. This is the amplitude, will tell me how far it will go, and this just tells me how fast it oscillates. So when this is very big, then there's going to be more and more oscillations, right? When this is very small, then I'm going to have less and less and less oscillations. If I have a different initial angle, what's going to happen is that this curve is going to be displaced either this way or this way. So for example, I could have something like this. It starts like that, and so on. And this is a mess. But the basic idea is this tells me how many waves per second. And remember, it's not really a wave. So this tells me how many oscillations per second, approximately. And this tells me where I'm starting my movement. Okay, now that we have the equation, we've pretty much done all of our work, because everything else is just mindlessly applying things that we are supposed to know already. Now, let me remind you that velocity is defined as the increase in displacement per unit time. But that's only really average velocity. The instant velocity, the velocity at each instant, is really only when this is extremely small, infinitely small. So we're really talking again about the derivative of x with respect to time. And thankfully, we know how to derive cosines now, and we know how to apply the chain rule, which is that when we have a thing with something inside, the thing inside goes outside. So let's do this slowly. Okay, so we want to find the velocity of this movement, and we know that it's just the derivative of this function. Okay, so the first thing that we need to do is to take a look at cosine. And we know that the cosine is going to turn into a sine. Actually, it's going to turn into minus sine, if you remember things correctly. If you forget these things, all you need to do is to draw. So here's my cosine. I know that it starts at 1. And then I look at the slope, and I figure out that the slope first goes down, so it's negative. And then I pi halves, I have 0. Sorry, I have minus 1, and that here I have 0. So this is exactly like a sine, but it's negative. So the derivative of a cosine has to be minus sine. Okay. So I'm going to have the amplitude, because remember that when I have a constant multiplying a derivative, it just stays there, doesn't do anything. So a times some stuff that I don't know yet, times minus sine, and I put a bracket here so that you see that it's multiplying, not subtracting, of omega t plus theta 0. Remember, omega is the angular velocity. And now we need to figure out what goes in here. And it's not as hard as it seems. Now remember that when we want to have a function inside a function, what we do is we derive a function. So for example, we have the cosine. We need to derive the cosine as if this was just x, and we get minus sine. And then we multiply by the derivative of whatever's inside, which is wt plus theta 0. Okay, now This is just a constant. So what's the derivative of a constant? Pause the video and yell it out. Yes, you said it right. It's 0. So this plays no role. And this is some number times t. So it's like some number times x when you're doing it with x, right? So what's the derivative of some number times t? Pause the video and tell me. Hopefully you said, yes, it's the number itself without the t. So it's this thing that just comes out multiplying. So this thing comes out of here and multiplies outside the sign. And there we go. That's it. This is the formula for the velocity in simple harmonic motion. It's minus the amplitude times the angular velocity times sine of omega t plus theta 0. And there we go. This is the velocity of a particle undergoing simple harmonic motion. And guys, you're not supposed to memorize this, but you will be asked to derive it in the exam. So make sure that you understand how to get from here to here. If you did not understand how to derive this, you need to practice your derivatives urgently. Cool. So now we have our velocity, and we can start noticing a few things, right? So for example, when this thing is 0, this thing is maximum. When this thing is maximum, this thing is 0, because that's just what the cosine and sine do, right? That they're opposite to each other. And that makes sense, because we know that when something is moving back and forth, at the very top, the velocity is 0. And at the very middle, the velocity is maximum when the position is 0. So it's exactly what we expect this to do. Great. And now we would like to find the acceleration. And for the acceleration, remember, it's just the increase in speed per unit time. So let's see where that leads us. So I'm going to make this little. And we have that the acceleration is the increase in speed divided by the increase in time. And again, that's just the average acceleration. If we want to know the acceleration at a given point, then we need to make this infinitely small, and we get the derivative. Exactly, very good. Okay, so the acceleration is just the derivative of the velocity. And we have the velocity, it's right here. So all we need to do is to derive this again. But hopefully now that we've done it for the cosine, this will be a little bit easier. So let's do it. Okay, so the acceleration will be, again, these two things are just numbers and I'm multiplying our function, so they just stay there without any change. So minus a omega times something we don't know times the derivative of this thing as if this thing was just an x. Now the derivative of a sine is just cosine, and this is just something you have to know, but if you don't know, remember you can always draw your graph and figure that out. So times the cosine of omega t plus theta 0. And now we need to decide what goes in here, and what goes in here is the derivative of what's inside here. And again, the derivative of what's inside here, that's 0, and that's just omega. So we need another omega over here. Cool. So we have that the acceleration is just this times omega times this. And we can make this look a little prettier. And we get then that the acceleration is minus the amplitude times omega squared cosine of omega t plus theta 0. And look, what's very, very, very interesting is that if you look at the equation for x and the equation for a, they're exactly the same. Look at the cosine. Cosine is exactly the same. Look at the a. It's exactly the same. The only thing that changes is this minus and this omega squared. So we can really write that the acceleration is just minus omega squared x. And that's truly remarkable. When we derive x twice, we get itself multiplied by some constant. And this is something that always happens in simple harmonic motion. In fact, this result is so important that we call it the defining equation of simple harmonic motion. When this happens, a equals minus omega squared x, then we know automatically that this movement is simple harmonic. So again, this is very, very important. Drill this into your heads. The acceleration is minus omega squared times x. And this equation defines simple harmonic motion. Every time that we find an equation that says that the acceleration of a particle equals some negative number times its position, we know that this particle is following simple harmonic motion. And we can know also how fast it's doing this, because this number will be the square root of the angular velocity. Now, a quick reminder about the angular velocity. The angular velocity of this thing is just about circular motion. So a lot of the time we will not be interested in the angular velocity. We will be more interested in the frequency, right? In how long it takes for this thing to go back. But if we know the angular velocity, we know the frequency. And let me remind you how these two things were related. If I know that something goes 1 revolution per second, then how much angle does it do per second? What's the angle of 1 revolution? Pause the video and tell me. Okay, so the angle of 1 revolution is exactly 2 pi. So if something has a frequency of 1, means that it's doing 1 revolution per second, then its angular velocity is 2 pi radians per second. Which means that to transform between this and the frequency, all we need to do is multiply by 2 pi. In particular, the angular velocity is just 2 pi times the frequency. And again, you have this in your data booklet, but you need to understand why this is so, and you can always deduce it like this. Cool. So now we finally found our defining equation of simple harmonic motion, A equals minus omega squared x. And what we would like to know is, okay, well, if I have a spring with a certain mass, so here's my spring, here's my mass, and this has a certain constant k. Can I use these two values to find the angular velocity of this motion? And the answer is, of course you can. And I'm going to show you how right now. Okay, so remember that when I have a spring, the force of a spring equals minus k times the displacement. Now, I can't exactly use this to derive this, but I can modify this very easily to get here. Now, what I would ask you to do is to stop the video and to try to do this yourself before I do it, because it's really, really simple. And if you see me do it, you'll just beat yourself up. Okay, hopefully you did what I asked you. I doubt it, but hopefully you did. And you figured out that the mass is really just mass times acceleration. And that's equal to minus kx. So then, of course, if I want the acceleration to be alone, all I need to do is to get this mass over to the other side. Remember, I just divide by m here, I divide by m here. So I get A equals minus k over m x. It's minus something times x. Minus something times x. This means that this will describe simple harmonic motion. What will be the angular frequency of this? What will be the angular velocity? Sorry, sometimes we call it angular frequency in physics, but never mind me. Angular velocity. Well, the angular velocity, this squared has to be equal to this number here. So, omega squared equals then k over m, which means that omega has to be equal to the square root of k over m. Now guys, you need to be able to derive this relationship. Almost every year there's an IB question saying, derive this relationship. It is not difficult to derive. All you need to do is compare two things and find, oh, these two have to be the same. So please, again, don't memorize this. It's completely useless. Learn to derive this, and you get that. And remember, sometimes you will see some movement that is not based on a spring, but it also has the shape of acceleration equals minus something times x. And as long as you remember that this is a defining equation of the simple harmonic motion, you will always be able to equal omega squared to wherever's in here, and then get the angular velocity. If you just insist on memorizing this, the moment that you are introduced to an example that has nothing to do with this, you'll be completely lost. Alright, so now it's time to use what we just learned in order to figure out how the energy of something that's moving in simple harmonic motion varies. Okay, so what we need to remember is that this thing, so if this is the amplitude, this thing is moving like that, right? So it's going from plus the amplitude, whether the displacement is plus the amplitude, to minus the amplitude. And this is a graph where I'm going to show you the potential energy as blue and the kinetic energy as red, and we're going to put them both as opposed to, like, against the position of the particle. Let's start with the potential energy, because I think that's going to be way easier. Okay, so with the potential energy, we know that it's just 1/2 of k times x squared. So what does that mean? Well, It means that when the thing is here, it's in the position of equilibrium, it's not getting pulled or pushed by the spring at all, so the potential energy is zero. As I try to stretch it, the spring is starting to act, do a force on it, right? I have to do some work to get it here. So if I actually let it go, it will have some energy and it will start oscillating. Which means that the more I stretch this thing, the more potential energy it's got. Right? And we just need to follow the formula. So when x is 0, that's 0. When x is a, which is the maximum possible amount, this will be 1/2 of k times a squared. Okay, good. So we see then that there will be a maximum value of the potential energy, which is 1/2 of k times the amplitude squared. And I'm going to put it over here. So this is 1/2 of k times the amplitude squared. And that's going to be maximum when x equals a, or when x equals minus a, right? Because minus a squared is just a squared. So this is going to be symmetrical around this, and we're going to have something that goes to 0 here and then back up. Okay, so let's do that. And there we go. Now for the kinetic energy, what we could do is look at how x depends, well, the v depends on x, and then figure this out using this equation. That would be a very stupid thing to do, but we could do this. Now the smart thing to do, of course, is remembering that the total energy must remain constant, and that at this point here, this guy has 0 velocity. So here, 0 velocity, which means that the kinetic energy is 0. As this thing loses potential energy, the kinetic energy gets bigger and bigger and bigger, until it reaches this point where the potential energy is 0, and therefore the kinetic energy has to be maximum. How much exactly? Well, if no energy is lost or gained, it has to be exactly equal to the maximum potential energy. So if I do a little bit of a dash here, well, that was supposed to be a dash line, I can draw the graph for the kinetic energy, and it will do exactly the opposite as the potential energy. So that when I add these two up, I will always get the maximum energy. And that's how a potential energy against position graph looks for simple harmonic motion. Now what happens if I have simple harmonic motion where the amplitude is half? How is this going to look like? Stop the video and tell me. Okay. Now if you said that this thing will be like this, like half the energy, you would have been wrong. And the reason for this is that this is squared, right? So if I have 1/2 of the amplitude, I really have 1/4 of the energy. So that is incorrect. And really, if I make the amplitude 1/2, then I would have 1/4 of the energy. So it would do something like this. And this again is a typical IB question. And that's just testing your ability to look at how things depend on each other. So if there's a squared and so on. Now, apart from this graph, there's another graph that I would like to look at, which is the change in kinetic energy, and then later on I'll look at potential energy, but it's the same thing, with time. So let me zoom out, and again I'm going to make a couple of axes. So here's whatever, and here's the kinetic energy. Okay, so first thing, well actually I think I'm going to make another set of axes so that we remember how the position evolved with time. Sorry, I did not mean to do this. Whoops. Alright, so just make a straight line instead. Okay. So remember that the position with time is a cosine function. So it starts here, then does this, then does this, does this, then does this, then does this, etc. And therefore the velocity with time does something like this. It starts here, and then remember that it's minus sign, so it goes over like this. So you can see that it's kind of like the same thing but out of phase by halves, which is exactly what we would expect, right? So when the position is maximum, the velocity is minimum. When the position is here, the velocity is maximum, and so on and so on. So now I would like to know the shape of the kinetic energy against time. So this is time, this is my kinetic energy, and I would like you to think about the shape of this graph, and also about the frequency of this graph compared to this one, right? So imagine that this has frequency of 1 Hertz. What's going to be the frequency of change in the kinetic energy? So stop the video and think things through before you start it again. Okay, well, hopefully you thought things through for a while, and you may have realized that the kinetic energy is 1/2 of mv squared. And this is very important, because when v is negative, v squared is positive, which means that in this graph here, this doesn't go down, this actually goes up, right? And then when it reaches here, it starts going down again to here. So let's just make a little line connecting these 2 points so we know where to finish. And then I'm going to make another line connecting these 2 points, and so on. Okay, so then this guy will start going down till it reaches 0, and then the velocity will start being positive, but again it's squared, right? So it will just go back. So we expect the velocity to actually do something, the kinetic energy to actually do something like this. And you can see that then the frequency of this thing is twice the frequency of here. So it's a very typical question in the IB. They will give you a kinetic energy graph and they will ask you about the frequency of the movement. And you need to remember that this is twice as fast, because all the negatives become positives here. And therefore this gets, for every 1 oscillation of this, you get 2 of this. Also, you need to remember that this is always positive. Now, if we wanted to draw the potential energy graph, we could do it 2 ways. One is also looking at this thing. We would have a certain shape here. And the other way is just by remembering that these two have to add up to always the same value. So if this is the maximum value, then the potential energy has to be the mirror image of this curve in order to always get the same. So we would have something like this, and so on and so on. And of course, if you look at what the blue thing does and square it, you will get exactly the same drawing that I have in here. So these are 2 ways of looking at the same thing. Right, now, before we finish with this, I would like to reintroduce a concept that we visited the other day when we were learning about oscillations, but I told you, just trust me on this will make no sense to you, blah, 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 blah. Well, now it's time to take a look at this now that we know the mathematics, and it will make a lot more sense to us. Now here we look at this equation. This thing here is an angle, okay? Now, because this is not really an angle in the sense that this is just something that depends on t, but we're not really spinning anywhere, we normally call this thing a phase, okay? And we call this thing here the initial phase, because this tells us where the thing is at the beginning. Okay, now it could be that 2 points, so for example, I have something that's oscillating, and at a given time, let's say t equals 1, this phase is, let's say, pi. And at another time, t equals 2, this is 2 pi. So the phase is difference, right? Well, we can actually calculate the difference between these 2 phases, and we call it the phase difference. So the phase difference is just the differences, so phase difference, excuse me, is just the difference between the phase at 2 points in time. Now, we will see this term phase difference in many other contexts, and for example, in a wave, this doesn't necessarily have to be time, because in a wave, this depends on position. So we have, again, a phase, but you can have a phase difference between 2 points that are oscillating. So one is oscillating like this, the other one's oscillating like that, but not synchronized, and then the 2 have an angle, and you can calculate the difference in angle, and that's the phase difference between these 2 points in the wave. And the phase difference is actually related to something called the path difference between 2 points, and then you can use this to calculate interference and whatnot. But the basic idea is that this is called the phase, and the phase difference between 2 points is just the differences between these angles that are inside the cosine, which is what allows our movement to describe the shape that we want. Alright, so far we've seen that the defining equation for simple harmonic motion is minus omega squared x. But as I told you, This not only happens for the spring, but it can happen for a bunch of different systems. Actually, there's many systems for which this is true, and therefore they undergo simple harmonic motion. And for each of these systems, the angular velocity is different. Just to give you an example, I'm going to show you how the simple pendulum, which remember is just a string with a little mass m balanced on it that oscillates like this, is an example that also oscillates using simple harmonic motion. Let me show you why. So the idea is that here we have this thing that's oscillating like this, back and forth, back and forth, back and forth, and there's a certain angle theta with the vertical, and this has a certain length L. And what we're interested in is to know how acceleration depends on x, and in this case x is going to be the length of this arc of circumference. So this thing here, let's call it x, is the arc of circumference that goes from the position of equilibrium until wherever we are. Now, of course, here there's two forces that we need to worry about. There's, on the one hand, the tension that's keeping this thing from breaking, and on the other hand, there's gravity that's going down. So let's draw these two forces. Here we have gravity, mg, and here we have the tension. Now, of course, what part of this force is making these oscillate? Well, it's not this part of the force, because this part of the force cancels out with the tension. It's actually this part of the force here. So it's this component of gravity that's actually getting this to oscillate. Now let's see if we can calculate this. All we need to do is we take this thing and we prolong it. So make this a little bigger. And then we know that this thing has two components. Component number one is this, that we don't care about, because this one goes against the tension, cancels out. But the one that we do care about is this one here. So it's this component here that points this way, and you can see that it's the same as this length over here, right? Now this is parallel to this, and this is parallel to this, so this angle is also theta. So let me just show that this is theta, and therefore this length here has to be equal to mg times the sine of theta. So the force that's propelling this thing back and forth is mg times the sine of theta. So let's see, tension, well, let's just say the total force is mg sine of theta. Now, it turns out that we are not interested really in theta, but we're interested in the angle itself. And we need to remember that an angle is nothing but a proportion. It's the proportion between the length of an arc and the radius of that. That's why, for example, when we have a circumference, the length of the arc is 2 pi r, and then when we divide by r, we get 2 pi, which is the whole angle of our circumference. So this angle here is nothing but x divided by L. So then the force is really mg sine of x divided by L. Good. And now we have a problem, right? Because we see that this thing is not proportional to x. It's proportional to the sine of x. And we need to start acting a little dirty. And by this I mean that we need to start doing what physicists call approximations, which is considering that this angle is really, really small, and if it's really small, then we can maybe simplify this a little bit. So remember then that wherever I derive from this, once I consider that this is really small, it's only going to work for small angles. So let's try that out. Alright, so what we need to do is just draw the little sphere that we always use for the sine and cosine. And I need to show you how to approximate this when theta is small. So here's theta. And remember that the angle is just this little thing, let's call it x, divided by this. Let's call it r. Okay, so theta is x over r, and that's just the definition of an angle. And if you still don't know the definition of an angle in radians, then you probably need to check that out. Okay, and how much is the sine of this angle? Well, the sine of the angle is really nothing but this height here, h, and then again divided over by r, right? So that's equal to h, and then divided by r. is the same thing. Now what happens when I make this very, very small? Well, when I make this very, very small, the curvature of this thing is almost nothing, right? So as you can see, let me just make a very small angle. So you have this arc here is almost the same as this height here. Can you see? These are almost the same. So x is more or less equal to h, which means that the angle, remember this is the angle, is more or less equal to the sine of the angle, because h over r is nothing but the sine of the angle. Which means that when theta is really small, sine of theta is more or less equal to theta. And if you don't believe me, try it for some angles. Just put some angle in radians, calculate the sine, and check for yourself that when the angle is very small, you get the same thing. Okay, so now I can use this and change things in here and get that force equals mg, and instead of sine of x over L, it's just x over L. And of course, force is nothing but mass times acceleration, so I have that mass times acceleration equals x over L. Now, the first thing that I notice is that the mass cancels out, which is always great news. So the mass goes out, and then I have that acceleration equals g over L x. And here, of course, I forgot the symbol, right? Because here you can see that the force is negative because it's going, well, it's positive because it's going this way, but my angle is negative. So here there should be a negative sign. So I should have added a negative sign here, here, and here. So I have that the acceleration equals minus g over L times x. Do you see how it's the same as this? So again, a negative thing times x, negative thing times x. So now I can use this to find the frequency of the movement. So let me zoom out again, and let's put these things together. So again, for a pendulum, I have that E equals minus g over L times x. And I also have that A for any simple harmonic motion is frequency squared times x, which means that this has to be equal to g over L. Therefore, the angular velocity has to be equal to square root of g over L. And now remember that this thing is also equal to 2 pi times the frequency. So 2 pi times the frequency equals square root of g over L, and therefore the frequency of a pendulum is 1 or 2 pi square root of g over L. And I would not have been able to deduce this if I had not known that this was simple harmonic motion, so that I could compare the angular velocity here with the angular velocity here. So you can see how this is some extremely powerful mathematical formalism. We can apply this to a great variety of situations, and actually most of the problems we can actually solve in physics are based in some form or another in the simple harmonic oscillator, something that just goes back and forth. Even in quantum mechanics, some of the most complicated stuff you're going to do is just lots of little simple harmonic oscillators next to each other. Most of material sciences is just lots of little harmonic oscillators next to each other. And it's remarkable the amount of things that we can do. By solving this very simple problem, we can solve a great number of very complex problems that we can turn into something that just goes back and forth. Okay, so we come to the end of the video. I'm afraid it was a really long video because there was lots of mathematical development. But I made it long. I could have made it shorter, but I think that making it long probably showed you more steps and made it a little bit easier to follow. That's what I'm hoping. Maybe I'm completely wrong. I hope I'm not. Anyway, so let's see if we did everything we were supposed to do. We saw this at the very beginning. We derived the equation for a moving mass in a spring. We used the derivatives to find the velocity and the acceleration, and we calculated the kinetic energy and the potential energy of a particle undergoing simple harmonic motion. And we did a bunch of other things that I think will also be useful in their own time. And now, without further ado, I'll leave you to do the problems, and I wish you good luck. See you guys later.